Good morning, good afternoon, good evening, ladies and gentlemen. Welcome to the next presentation. The topic today, silicon carbide, the sustainable solution for various applications. My name is Tobias Keller and I'm the Global Head of Product Management at Hitachi Energy. Let's start at the beginning with three things good to know. As mentioned, my name is Tobias Keller. I'm located in Lenzburg in Switzerland. I have more than 23 years experience in power semiconductors. If you would like to reach out to me, you'll find here my email address. Hitachi Energy is a global player for sustainable transmission, mobility and distribution. We are currently a joint venture owned 80.1% by Hitachi and 19.9% by ABB. We are the former ABB Power Grids division. As of 1st of January 2023, we will be 100% owned by Hitachi. We are 40,000 employees in more than 90 countries, a real global player, and our headquarters in Zurich in Switzerland. If we go a little bit into the history of Hitachi Energy Semiconductor, we started the semiconductor application in 1913 with the first mercury arc rectifier for a traction infrastructure application, well-known Jungfrau Railway. In 1939 we advanced with high voltage DC, started in 1996 with the IGBT and started our activities with silicon carbide and silicon carbide chipsets in 2000. 2021, as mentioned above, former ABB Semiconductor became part of Hitachi Energy. I'd like to give you today an overview of various applications where silicon carbide is already the standard, and we expect to become the standard pretty soon. Go into the topic of addressing the high performance requirements and reliability with Hitachi Energy's High K, and then close with two devices on 6.5 kilovolt and 10 kilovolt for future applications. Let's start with some facts. Silicon carbide has found its way into e-mobility for cars, bus and trucks. There are obvious reasons why it is like this and huge advantages using silicon carbide here. Obvious on cars, bus and trucks, it's all about driving longer or longer distance with the same energy stored in the battery. And in the charging application, what is very close and very strongly related obviously to the car, bus and truck application, it's a charge faster with less losses. How can that be done with silicon carbide? With silicon carbide we can increase the switching speed up to 20 kHz. That means any filter chokes and caps what are required will be smaller, and we see also a clear trend that the RDS zone is significantly reducing over time with new chipsets. At the same time, we see much higher current density. What is possible in the same package with silicon carbide, we can increase the current with factor 2 compared to silicon. And new connection technologies, of course, also handle these higher currents. And we have significantly lower losses, and in future we can also go much higher in the junction temperature. Instead of 125, 150 as known from silicon, we are already at 175 these days and can go up to 200 degrees centigrade continuous in the future. Obviously there is also a second part on e-mobility. Thinking about traction, rolling stock, using power electronics for a long time already, also now more and more preparing for silicon carbide. But there is a significant difference, and this is the reliability. While a car is built for several 100,000 kilometers and let's say several 100,000 power cycles, a loco or even a heavy mining vehicle is built for millions of kilometers and therefore also millions of power cycles. As an example here, one of our longest living diode is in operation for more than 45 years. And what is also different, demanding environment and conditions in terms of vibrations as well as in terms of temperature. From a performance point of view, the power is significantly higher. We are talking about 1 megawatt to 9 megawatt. And we have also some additional demanding operation condition in a loco as an example, the so-called Ponto bounce. You might have seen it when there is ice or snow on the catenary, there is the so-called Panto bounce, what gives a lot of disturbances directly to the power semiconductors. But there are also other applications where silicon carbide is developing into. If you have a look at today's power grid, all the red marked areas are already containing power semiconductors. If you would go another 10 to 15 years back in time and would have had a look at the power grid at that time, you would haven't seen these red marks. And of course, if you go 5 to 10 years into the future, you will see even more of it. And power electronic finds its way, of course, from the application, as we already discussed, but also from the charging for this application towards the connection, where different power grids are connected together with solid state transformers, with AC connections, or HVDC transmission power. Very interesting to know, here we are talking about voltages of 800,000 volts and transmission power of 8 gigawatts. Last but not least, also in the power generation, power electronics finds its way. Here as an example, offshore wind turbines with today a power up to 15 megawatt. And these are all applications where silicon carbide might bring certain advantages. Very obvious, having a look at this application, there is a lot of demand on high performance and reliability. Hitachi Energy is addressing these both requests with its high-K technology. That means, despite using a silicon oxide gate stack, Hitachi Energy is using it in its silicon carbide device as a high-K stack. And with high-K and high mobility, we can reach lower channel resistance, what is one of the main contributors to the overall resistance in a silicon carbide MOSFET. And at the same time, as it is shown later, we can increase the reliability of the device itself. Here, as an example, dynamic stability test for repetitive gate sweep in RBSOA with plus minus 15 volt. With the high-K technology, we see no drift over time in turn off and a very limited drift in turn on, what makes it an extremely reliable device. Furthermore, an important aspect on silicon carbide MOSFETs is the safe operating area. As we all know, in high power and high voltage applications with silicon power semiconductors, we were in the range of 10 microseconds SOA. Here we see various curves, various recordings for 1.2, 1.7 and 3.3 kilovolt devices. And this is very important for any application you might think about in a power grid. Let's have a look at the very high voltage devices. We have seen 1.2, 1.7 and 3.3 kilovolt silicon carbide devices with high-K technology. For application in grid, you need also higher voltage devices such as 6.5 kilovolt, even in the e-mobility application. In traction, 6.5 kilovolt MOSFETs are finding an important application. And you see here MOSFET turn on, turn off from devices we have built at Hitachi Energy. And if you go even one step further and think about building HVDC or solid state transformers with very high voltage, there might be the need for a 10 kilovolt silicon carbide MOSFET. Also, if you plan to build a transformerless locomotive, such devices would be extremely helpful. And these are some switching curves from first devices we have built with high-K 10 kilovolt gate stack at Hitachi Energy. Thanks a lot for your participation. Thanks a lot for listening to me. I'm looking forward to question and answer session afterwards. Thank you.